Okay, we reached the final video in our series of 4 videos. Am I ready for Math 104? 5 questions each video. This is the last 5. This one is about an optimization question where we have some quantity we want to optimize, find the max or min of. And this particular question is about a box made from an 8 by 8 inch piece of cardboard. And so square cardboard, 8 by 8 inch, and we're going to cut off squares from the corners. So we're going to cut a square. Let's do dotted lines for cutting squares. So we're going to assume that each one of these guys are identical, although in my picture it might not look like it. And we're going to cut those out and then fold up the sides. And this piece is going to be gone, 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 and gone, and we'll have that ability to fold up the sides and have this be sort of the bottom part, and then this will be the bottom, and then we have the left, right, front, and back. Once we fold that up, and we'll have our box. So what we're going to do is say that this entire distance was 8, but we're losing part of that, and it's inches. We're losing part of that. We're going to cut off some square. Let's call the square x by x, each one of these squares. And so we don't know where to cut it at, but that's what we're going to end up finding out. What does x needs to be? What size squares should be cut out to create a box with the maximum volume? And so the box, once it's all folded up, let me just draw something to represent that. Once it's all folded up, we'll have an open top box, and it'll have a volume to it. The bottom is made up of a square where we have 8, but we take away x on both sides, so 8 minus 2x will be the dimensions for the bottom. And then the part that gets folded up will have, the box will have a height of x. And so the volume of that box will be x times 8 minus 2x, basically squared. Length times width times height. And it's our job to maximize this. And to do that, then I'm going to take the derivative, set equal to 0, and argue why it's going to occur at a critical point. And so what would be the best way to do this? Should we multiply it out? Just get a nice polynomial. We get 64 minus 32x plus 4x squared. And so 64x minus 32x squared plus 4x cubed will be your volume based on x. Nice formula. The derivative of that would be 64 minus 64x plus 12x squared. We want to set that equal to 0. Let's take out something so the numbers are smaller. Each one of these guys share a factor of 4. And so we take out a 4 and we're left with, let's write it in decreasing order, 3x squared minus 16x plus 16 equals to 0. And hopefully this is some nice thing to factor. 3x and x, 8, and oh, the signs are the same. It's minus and minus. So yeah, 8 and 2 don't work. 4 and 4. 4 and 4 work. That would give us x being equal to 4, or possibly x being equal to 4/3. So one of these is a bad answer. imagine if x was 4, you'd cut out 4, and you'd cut out 4, and you wouldn't have a box. So x couldn't be 4. So x is 4/3. Now, that's the value that would make the derivative 0. What we need to show basically is that this local maximum that we'll be getting at 4/3, this local maximum that we'll get is actually an absolute maximum. We have to prove that we have a max, and then we have to answer the question. So what happens on the left-hand side of this, your derivative would be, if I plug something like a 0 in, your derivative would be positive. And then if you plug 100 in, your derivative, or even something smaller, I guess I should actually put this 4 in here, although it's unrealistic. This is back to being positive again, but in between it's negative. We have a local max and a local min, but we need to show why this is an absolute max, and we can argue that by talking about how the second derivative, which is going to be a negative 64 plus 24x. Well, now that's going to change sign too. So, can't argue with that. If your second derivative didn't change sign, that would be proof that you have a absolute max. So, abandon that. And when x is 4/3, we have a local max. We can do a chart basically and say that we know we can't be equal to 0, we wouldn't have a box, and we can't be equal to 4, we wouldn't have a box. And so these lead to 0 volumes, and so it has to be something between 0 and 4. X can't go past 4, and then when we have 4/3, your volume will be the maximum. The local max will be an absolute max. They don't want us to find this volume, but it'll be some positive value. The dimensions of the box, what size squares should you cut out? They'll be 4/3 inch by 4/3 inch. Letter F. That took way too long. Probably chop this into 2 parts, but that's the answer to the question. We take the interval from -1 to 1 and we chop it into 4 parts, 4 equal subintervals. So right in the middle would be 0, and then in between those guys would be a half and -1/2. Okay, how this works is this function 2x plus 1 is actually a upward sloping line. And we want to find the value of the Riemann sum. And the Riemann sum is by doing right endpoints. At every interval, you'll be doing the right endpoint. And so we go up and we touch the function. And then to find the height of these rectangles that we're going to get, we're going to use the right endpoint. And so the change in x, the delta x, is always going to be a half. Each of these rectangles has a width of a half, and so the height, though, the height is done by going to the right endpoint. And so what we're going to do is take the function at -1/2 times a half. That would be rectangle 1. So that would be this rectangle, and we add the function at 0 times a half. That would be that rectangle 2. The function at a half times a half, that would be that rectangle there. And then finally the function at 1 times a half. That's what that Riemann sum represents. Basically R1 plus R2 plus R3 plus R4 rectangle areas. And that's what they want us to find. You can factor out the half, it's in every one, and then let's find out what these function values are and add them up. So we're plugging into the function who is called 2x plus 1. So if we plug a negative 1/2 in, what we get is a 0. Negative 1/2 that gets doubled and added on to 1, we get 0. Plug a 0 in, we get 1. Plug a 1/2 in, we get 2. And plug a 1 in, we get 3. Sorry about that. What just happened? Sorry. There we go. And then add these guys up, and we get 6. So the total area would be 3. It's an approximation. Okay, it is an over approximation. The true answer will be found to be smaller than that. And we get that by integration. Integrate 2x plus 1 from negative 1 to 1. That would be the actual answer. And ours is an approximation to that. Okay, great. In the interest of time, I need to chop this up. And well, let's see this next question. Yeah. So let's stop this video and then we'll do one more.